Okay, we're going to continue on with the Chapter 16 thermo problems, and we're going to look at the concept of Gibbs free energy. So Gibbs free energy is, it's a tough one to really wrap your head around, but essentially what it is we've been using it in standard state. So this little standard state symbol means at 1 atm in 298 Kelvin. Okay, and what we said is that if delta G, when we're talking about standard state, if that is less than 0, then the reaction is spontaneous. If it's greater than 0, then the reaction is not spontaneous. But there's more to what this delta G is. The Gibbs free energy is an indicator of, in this reaction, does the reaction have energy that is available to be used to do work, and useful work, like maybe we could use this reaction and get some work out of the reaction to do something else, like power a device, something like that. Now, there's a couple of equations that are associated with this delta G, but we're going to look at this one here to start. So the delta G, if we're not at standard state, is going to equal the delta G at standard state plus this correction factor, RT ln of Q. And this Q, that's the reaction quotient from equilibrium. So remember, that's what are the concentrations of the products over the concentrations of the reactants. And if all of the pressures that we're talking about, because we're going to only deal with this in terms of pressure, which is why there's this RT here. So if you remember from the equilibrium, that RT was a multiplier when we went back and forth from pressure to concentration. But if all the pressures are equal to 1 atm, well, 1 atm, that's standard state. So if all of the pressures are at 1 atm, then ln of Q, right? Q is going to equal 1 time raised to some power over 1 to some power, or maybe there's a couple of ones, like in this case it would be 1 times 1 over 1 times 1, right? And so you'd get Q is equal to 1. But let's think about what that formula is going to do. ln of 1 is equal to 0, right? Because remember, E raised to the 0 equals 1. So anytime all of the pressures are equal to 1 atm, you're at standard state. And if you're at standard state, then your delta G should equal the delta G at standard state. And that's why this thing becomes 0 when all of the pressures are 1. Okay, but let's just walk through number 55. I'm only going to do 57 rather. I'll do 57 on this video, and then I'll do the rest of them on the next video, because I wanted to give you a little bit of intro on that Gibbs free energy. So 57 says, use the data from Appendix 4 for this reaction up here. And then the temperature is going to be 298 Kelvin. And it tells us that the pressure of the NO, and I'll just write these above it, the pressure of the NO is 1.00 times 10 to the minus 6 atm, and the pressure of the O3 is 2.00 times 10 to the minus 6 atm, and pressure of NO2 is 1.00 times 10 to the minus 7, and the pressure of the O2 is 1.00 times 10 to the minus 3. And we're asked to find delta G. And it says use Appendix 4, so Appendix 4 is going to be helpful to get delta G in standard state. Okay, so we're going to first go to Appendix 4 and find delta G in standard state, and we know how to do that. It's N of the products times the delta G standard of the products minus the sum of N of the reactants times delta G standard of the reactants. And so when we do that, I looked them up. We have products 1 times the delta G of the NO2 plus 1 times the delta G of the O2, which we know that's 0, minus 1 times the delta G of the NO plus 1 times the delta G of the O3. And when I plug these numbers in, it's 52 minus, in parentheses, 87 plus 163. And so my delta G in standard state comes out to be negative 198. Now be careful because this is kilojoules per mole. When I use this equation, I have to change the delta G's to joules per mole because, and I'm just going to change it right here, it's 198,000, negative 198,000 joules per mole. Because remember, this R, that's the gas constant, that's 8.314 joules per mole, joules per mole Kelvin, I believe. Okay, and then this would be Kelvin, and that would come out right. So in order to use the delta G standard here, we have to get it into joules, not kilojoules. Okay, so we're asked to find delta G from our delta G standard now. So we're going to say delta G is equal to negative 198,000 plus 8.314, and this is joules per mole Kelvin, times T, and we were told in this problem T is 298 Kelvin, times the ln of Q. So what's Q going to be? Well, let's calculate Q outside and then we'll plug it in here, okay? So Q is going to be the pressure of the NO2 times the pressure of the O2 over the pressure of the NO times the pressure of the O3. And so when I put those numbers in, I get 1 times 10 to the minus 7 times 1 times 10 to the minus 3 over 1 times 10 to the minus 6 times 2 times 10 to the minus 6. And when I do that on my calculator, get the calculator here, 1 negative 7 times 1, second E, times 10 to the negative 3, divided by, in parentheses, 1 times 10 to the negative 6 times 2 times 10 to the negative 6, and I get 50. So Q is equal to 50. So we'll plug that Q in here. And then we're just going to run that equation on the calculator. So we're going to put in negative 198,000 plus, in parentheses, 8.314 times 298 times ln, I don't need the second, ln of 50, and I have 2 sets of parentheses there, and so I get that delta G at these conditions, 298 Kelvin, and the pressures that were given, is equal to negative 188,308 joules per mole, but we write that in kilojoules, and because of the sig figs, we're going to round that to 3 sig figs. We were given 3 in most of the given information. And that's how you use that equation. And so the delta G in this situation that was given is negative, meaning that this reaction is still spontaneous at this situation. Okay, I'm going to do the others on the next movie to make it not so long that you can sort of skip through.